All right, the next section we have here is implicit differentiation. This section is how to differentiate equations that can't explicitly be solved for the dependent variable, or maybe equations that solving for it is possible, but maybe you just don't want to do it, or maybe it's very hard. So that's what implicit differentiation allows us to do. This arises naturally in many ways because many things, many relationships are not functional relationships. For instance, the graph of a circle is not a function. It fails the vertical line test, but there are circumstances where it would be useful to know the equation of the tangent line, or at least the slope of the tangent line, to different points on that curve. So you can go ahead and read this if you'd like. I'll walk through an example here, but we'll just go ahead and get started with example 1 here. So at example 1, we want to determine the equation of the tangent line to the unit circle at the point 3/5, 4/5. So to do this, we need to start with the equation of the unit circle, which is x squared plus y squared equals 1. So once we have our equation, we're now ready to differentiate. So we'll go ahead and differentiate each side of the equation. So you got to do it to both sides. Just like adding something to an equation, you have to add it to both sides. So the right-hand side is straightforward. Derivative of a constant is 0. On this side, this first derivative is straightforward. That's going to be 2x plus, and now here is where we run into our little thing that we have to worry about a little bit. So whenever we have something like this, ddx, this is saying take the derivative of whatever is in front of it, so this thing in this context, with respect to this variable. So in other words, you're treating this as the variable. So if you encounter anything else that's not that's not an x, then you treat it as a constant. That's always true for a derivative. This is a declaration of what the variable is. However, in this case, whenever you have an equation, and in this case, let's say we have an equation with two variables. Well, if we have an equation with two variables, if I tell you what the x value is, does that mean y can be anything now? No. If I say x is 0, then y is either -1 or +1. So it's not truly that both x and y are independent variables. We can treat one of them as independent, and then the other one is dependent, even though we didn't have this equation solved for y. So in actuality, in this equation, although we're not writing this as y expressed as a function of x, we say that y is implicitly a function of x. So in that case, what we can really do is we can think that y is just some function of x. So when we have a term like y squared, this is really saying take the derivative of this function y of x quantity squared. What's the chain rule say to do? Chain rule, derivative of the outside, leave the inside alone, multiply by the derivative of the inside. So effectively, that's what we're going to do here. But using this of x notation, the parentheses with the x, that makes it kind of clunky and cumbersome to carry out. So nobody really uses this notation when you're doing implicit differentiation. We would just keep it as a y. So our work here would look a little bit more like take the derivative of y squared with respect to x, and then you would get 2y y prime. And remember that y prime is the same thing as dy dx. For me, I use dy dx notation pretty much always, so you won't see me using this a ton, but I know some people are fond of that. So this is really what we're going to be doing here. So let's go ahead and try that out. We don't have to do anything fancy here because the x's match. It's the correct variable. Here, there is a mismatch, so to speak. So we would differentiate as normal But then, because there's a mismatch, y and x are different, we're going to have to compensate by tacking this on. And technically, you can think of always doing this. Like over here, after we differentiated this, technically we should have had a dx dx, but this is saying what's the derivative of x with respect to x? Well, derivative of x with respect to x is just 1, so that's why we don't write it. You never notice it. So if it helps you, you can think of it, you can think as if we're always doing that. Okay, so once we're here, depending on what your problem is, like how it's worded, you may have to solve for this dy dx. So I'll go ahead and just show you what happens if we solve. So if we choose to solve for dy dx, so solving for dy dx, in this example, we technically don't have to solve for it first. We want to know the derivative at this point, 3/5 comma 4/5. So because we don't want the derivative in terms of any arbitrary x and y, we only want to know the derivative dy dx at this specific x and y pair. We technically could plug in 3/5 and 4/5 at this stage. That would make it easier to solve for dy dx. Some problems, though, they just ask you to find dy dx, and they don't necessarily want dy dx at a specific point, in which case you couldn't plug in anything for the x's and y's. You would just have to solve for dy dx first. So I'm going to show that anyway, just because you're going to have to do it eventually anyway. So let's get started here. So I'll go ahead and divide each side of the equation by 2. And then I'll solve for dy dx by subtracting the x to the other side and then dividing by the coefficient. So now once we have that, we want to evaluate the derivative dy dx at the given point. So for us, that's 3/5, 4/5. So if we go ahead and plug that in, dy dx equals negative, we have 3/5 divided by 4/5, but division by a fraction is multiplication by the reciprocal, so this should end up being dy dx equals negative 3/4. So that's the slope of the tangent line, but now we need the equation of the tangent line, so we'll go ahead and just do point slope form. Y minus the y coordinate, which is given to us, it's 4/5, equals our slope, negative 3/4, times x minus our x coordinate, which was given to us, 3/5.